Okay, so in this class, we're going to look at RC and RL circuits. So the first thing is to understand what RC here and what RL, what they represent. So this is going to be the resistor capacitor circuits. And then RL is going to be the resistor inductor circuits. CCT, that's just going to be for circuit. So this is what we want to see. We want to see how we handle this type of circuits. And to a large extent, the treatment of these circuits is going to be similar to just normal resistors or the circuits that we've been looking at so far in this course. But there's just going to be some slight adjustments. So for starters, we want to focus on just primitive circuits where we only have, let's say, a capacitor, so that we understand the treatment of a capacitor when it occurs in a circuit. So that is what we want to see. So let's take a capacitor, or let's first try to understand what a capacitor is. So for starters, let's focus on the RC circuit, the resistor capacitor circuit. But first, want to understand what a capacitor is. By definition, a capacitor is just a passive element. For its design, it is basically just designed to do one thing: to store small amounts of charge or to store energy. Now it stores energy in its electric field. Now what happens? So for a capacitor to be made, usually you have two plates, something like this. Sometimes you're going to have some material between the two plates, but all in all, sometimes we'll just be left to say the material inside is air. But one plate will be connected to a source. This will also be connected to the opposite terminal of the source. So let's look at a case where you connect this to a positive this side and a negative this side, a source in that manner. So what will happen in this case is that this capacitor, of course, these are two conducting plates here. So the two plates, this one and this one, these are conductors. So what will happen when they are connected to a source like this plate is going to be charged, and the charge it is going to accumulate is going to be a positive charge, or this is going to accumulate a negative charge. So here, this capacitor now has been charged. In a circuit, a capacitor is going to be represented by two parallel lines. So you're going to have a line this side and a line this side. So this is going to be the circuit symbol for a capacitor. But for this one that we have drawn here, in this capacitor, we can say current is going this side, and then we have the capacitance of the capacitor. Basically, here, the capacitance, we're going to see exactly what it is, but it's a property characteristic of a capacitor. So whenever a capacitor is given in a circuit, they're going to tell us its characteristic value, that capacitor C. So we're going to have that there. So for a capacitor like this one, this is going to be a capacitor whose capacitance is constant. If we're given a capacitor and then you have this part here in a circuit, and then they give something like this here. In this case, it is a capacitor still, but now its capacitance is not a constant. It can be changed. So this is a variable capacitor. So similar to a variable resistor, if you think about it, for a variable resistor, we had something like this. Then we just had something like that. That was a variable resistor. So the same thing, it's basically the same capacitance symbol, but with an arrowhead like that. Okay, so we did say a capacitor is a passive device, a passive element that is used to store charge. the amount of charge that a capacitor is going to store varies, or it depends on how much the voltage is where it is connected. Take this circuit, for example. How much charge is going to be stored by this capacitor depends on how much voltage we connect it to this side when we are charging it. So in this case, this is going to be the relationship. And when we change this proportionality to an equal sign, this expression reduces to the charge stored in a capacitor being equal to a constant of proportionality C, which becomes the capacitance, multiplying the voltage that we used there. So this becomes the voltage that the capacitor gets to store. And then, of course, this is going to tell us how much charge the capacitor is going to keep. So basically, from this expression, we're seeing that the amount of charge stored in a capacitor depends on how much voltage was supplied to it when we were charging the capacitor. So basically, this is what we get. Then this constant C, the capacitance, has units of farads. So those are going to be the units of the capacitance C. Now, this expression that we have just come up with, the one that tells us how much charge a capacitor stores, we're going to hold on to it. It's going to be among the important expressions or whenever we're dealing with capacitors. And when we look at that, we have charge is equals to capacitance times voltage. If we are to get the derivative of the charge with respect to time, let's say we try to measure the amount of charge that is coming or that is passing a specific point in some period of time. C here is a constant, so we can easily bypass it. But the voltage there will also vary with respect to time. So we end up with dV dt this side. But if you have the rate of change of charge with respect to time, notice that this is the definition of current. Current is the change of charge with respect to time. Based on that, we can now see that this part is just current. And this will be equals to C dV dt. So we have just seen that the current that is going to be passing through that capacitor can now be expressed as the product of the capacitance multiplying the change of voltage with respect to time. This becomes expression number 2 that we need to pay attention to. With the current obtained, everything else really becomes straightforward. Because if we wanted to get the voltage from here, just make dV the subject of the formula. If you cross multiply here, you're going to have dV is equal to, it's going to be, so we're going to have 1 over C, because of course it's going to divide both sides by C. Then we're going to have current multiplying dt. Here, you're just making dV the subject. It comes to look like this. When you integrate both sides, you see that the expression for the voltage can now be seen as 1 over C is a constant, since C is a constant there. So this will now be the integral of current with respect to time. But for this one, of course, you know to say when integrating, it's going to be from time is equals to 0 to some value of time t. But here you have to also take account of how much voltage was present when you were starting, meaning how much voltage was present at t is equals to 0. This expression becomes what you would want to use when you want to calculate the voltage this time. Again, notice that all these expressions I'm coming up with, they are all coming from one equation, the definition of the stored charge. From the stored charge, by differentiating charge, we got what? We got the current. By integrating, making dV subject and integrating, we have come up with the expression for voltage. In the same way, we can recall that in electricity, power is equals to voltage times current. So where there is current, if I put the expression for current, I'll have voltage. Current, we saw current was what? C dV dt. So I'll have C dV dt. So that now we can say that power is equals to the capacitance V dV dt. So we have just come up with the expression for power, just like that. So this is how this is reducing. And from the expression for power, we can easily come up with the expression for work done, because we know that power is equals to work done over time. So I can even say, we can express this as d work over dt as the expression for power. But we know to say power can be obtained as this, so that now we can view this as CV dV dt equal to the rate of change of work with respect to time. Let's get the rate of change of work. Here the dt can be seen to come out from this expression, so that now we have the work done being equals to CV dV. And then work done, when you integrate, you now have C is a constant, it comes out, and then this is just V dV. So you can now say the work done when you integrate this can be seen. So you can take it from T is equals to, so usually this, when working out with this one, usually we start from minus infinity up to some time T. So basically from the beginning altogether. That is why we don't say, we're not going to include the amount of work which was initially present, because we're saying we're going to start basically from as low as possible. But all in all, even by just not looking at those limits of integration, just look at the integration there. Let me just remove this in case they are confusing you. Just look at the integration there, because above all, those limits of integration are in terms of t, but this is basically only has a v there. When you integrate v there with respect to v, you're going to get to the power, currently it's a 1, add 1 becomes 2, then divide by the same thing, 2. What are we seeing? The work done becomes 1 over 2 CV squared. And there we have it. We've just come up with another expression. So here, notice that I was just playing with these equations. It was basically the same equation that I was using, and then I was able to come up with all the others, 4 and finally 5. Okay, so for a capacitor, basically this is how the equations will turn out. Now, how about if you're playing with a capacitor? What happens? How do you get the work done? Sorry, that's not the capacitor. Just from looking at the capacitor. So moving on to an inductor now. So how do you get the current through an inductor? How do you get, or first, what is an inductor? And how do you account for the power stored being given out from an inductor? Just like a capacitor, an inductor is also a passive element designed to store energy in its magnetic field. Remember, the capacitor was storing energy in its magnetic field as well, and it stored energy in form of charge. Here, an inductor will also store energy. And how does it really work? So what would happen for an inductor is, in a circuit, an inductor, it kind of looks like a resistor, but weirdly, like this. So this is the circuit symbol for an inductor. So the constant here is going to be taken as L. If current is going this way, the part where current reaches the inductor first will be positive, and where current will be leaving from will be the negative part. The constant here is going to be L. Now, for an inductor, what happens really? What is it doing there? In a capacitor, we saw that the amount of charge stored was proportional to the voltage supplied. And then from here, that is how we ended up with Q is equals to C times the supplied voltage. For an inductor, the voltage across the inductor, the voltage across this inductor, let's label that voltage as V. So the voltage across an inductor will be proportional directly to the time rate, or the time rate of change of current. Basically, we're saying the voltage will be proportional to the change of current with respect to time. And directly from here, when you change the proportionality to an equal sign, we see that we introduce a constant, and that is going to be the inductance, L. And this will still be I dt. Notice that just from the definition of what the inductor does, we come up with an equation for an inductor that kind of looks like equation 1 for a capacitor. For a capacitor first, not equation 1, equation 2. For a capacitor first, we had this from the definition, and we only ended up with I is equals to C dV dt after differentiating. But instead of this, for an inductor, we're now saying it is V. Instead of C, we're saying it is L. Instead of dV dt, we're saying that they've swapped. V, which is here, is now this side. I, which is here, it's now the one being differentiated, di dt. So I hope you're seeing this. By knowing one equation, you can easily remember the other. For a capacitor, the current coming from the capacitor is C dV dt. For an inductor, the voltage discharge will be equals to the inductance di dt. So find a way of relating them. It makes it easy for you to remember these formulas. Otherwise, they can be easy to forget. And once you have this expression for voltage, it becomes easy for you to get the current coming from there, because again, just make the I subject. The V will multiply the dt, then the L will go down. We end up with something like this. Then integrate both sides. 1 over L will be outside the integral. This is going to be from time is equals to 0, the initial time to some time t, V dV. Then plus the initial current that was present at t is equals to 0. So this becomes the expression for getting the current. In the same way, we can get power. Power is VI. And then from power, here, we're not going to substitute I, because look at how weird I looks like. So the one we'll be plugging in here will be V. V was L di dt. So it will be L di dt as V, then multiplying I. So you see that power becomes equal to L I di dt. That becomes the expression for power. In the same way, power can be related to the amount of work done in a specific amount of time. So just like that, we can get the amount of work by integrating power. So the amount of work will be the integral of power. We saw power was what? L I di dt. But we see that we have to multiply this with dt. dt falls off, so that now this is just the integral. L is a constant, I di. So from here, when we integrate I, we see that this is going to be 1 over 2 Li squared. This becomes the expression for the power stored. Now, the next thing we're going to look at is how we actually work with these formulas we have come up with. So that leads us to the first one is going to be the source-free circuits. Source-free, RC and RL circuits. The ones that we'll focus on are going to be first order equations. our first order, yeah, expressions. So they are basically the easy ones. Then it's possible to get the weird ones, but I think for the coverage of this course, we don't get the weird ones.